I hope you guys are ready for some more boring math. Hopefully not too boring. All right, so I believe that Doug already talked a little bit about this earlier today. What? What? Sit up. Oh, no. Oh, sorry about that. Better? All right. Let's do it. Correction for multiple comparisons. Are you guys aware of this problem? Not necessarily in neuroimaging or cortical thickness analysis or fMRI, but in general, which is that what's a p-value, right? If you think about it, it's in principle, p-value is a probability, right? It's the probability that you can reject, or the confidence with which you can reject your null hypothesis. Now, if the p-value is very small, it essentially tells you, for example, if your p-value is 0.01, it means there's a probability 0.01 that this observation happened due to chance, right? So if that p-value is very small, you can say, well, it probably wasn't because of chance, it's because the effect is actually there, right? Now the problem is that if you remember, we are fitting a GLM for each point on the surface, and that's like over 100,000 points. So, of course, if you got a p-value that was say 0.01, you could naively say, oh, this guy is significant, right? Because it has small p-value, but that's unfair because you are like somehow rolling the dice so many times, like hundreds of thousands of times. So it's going to happen that by chance you're going to observe an effect sooner or later, right? It's just like too many voxels that you're observing in fMRI, or too many vertices on your surface that you're observing. So what you would do normally in statistics is that if you could use Bonferroni correction, right? That's the easiest thing to do. So you would say, okay, if I'm observing 100,000 vertices and my significance threshold is 0.01 normally, I will have to divide that threshold by 100,000. The problem with Bonferroni is that if you do that, you're not going to get significance anywhere because your threshold is going to be too aggressive. And the reason for this is that when you do Bonferroni correction, you're assuming that your different experiments are independent. And that's clearly not the case, right? In our neuroimaging studies. Like, if you're looking at fMRI data, like neighboring voxels tend to have similar responses, and same thing with thickness, right? When we look at the cortical thickness, it's not the case that you have a vertex here that has thickness 3 millimeters, and next to it another one has a completely independent measurement. That's not true, right? So there is smarter stuff that we can do, and that's what we're going to discuss now. This is very important because it's very easy to cheat, even unconsciously, if you're not aware of how the correction for multiple comparisons work. So this is an important topic. So okay, this example we have here to start with is this fMRI activation, right? Like I said, if I just look at voxels that have a p-value lower than 0.1, right? This threshold is not aggressive at all, 0.1. And then what do I get? I get some regions that look like, have meaningful activation, but I also get a lot of like, dirt in the background. And we know there is no activation in the background, right? There is no fMRI, there's no activity. So this threshold seems to be a bit too liberal, right? You can increase the threshold, right? And you will get something like this. And now you have like some clusters that are still there, right? Inside the brain that looks like, well, there's probably activation here. If you ask me, like my gut feeling looking at these pictures. But obviously this threshold is still not aggressive enough because, or maybe it is, I don't know, but you have still a lot of dirt in the background. I cannot definitely say that every voxel that is yellow here has meaningful activation, right? And if I go all the way to 10 to the power of minus 7, then, well, I'm pretty confident that these areas will be activated, but then I'll be wondering whether I left out something that was actually meaningful, and I just erased it because I was too aggressive, right? So it's sometimes difficult to find a balance between having a threshold that is too conservative and a threshold that is too liberal. So there is something else we can do, right? And that's analyzing clusters. Because like I said before, our data is intrinsically smooth. Like neighboring voxels are going to have similar activations, similar points on the surface are going to have similar neighboring points on the surface are going to have similar thicknesses, right? So the tree signal, like it says on the slide, tends to be clustered. So true positives are usually, grouped, clustering around each other, but false positives are usually randomly distributed. And that's what you are seeing here, right? So can we forget about our Bonferroni correction and about the vertex-wise or voxel-wise p-values and move to a cluster analysis and get better results? And the answer is yes, okay? So the first thing when we're going to do cluster analysis is to find the initial threshold, the clustering threshold. And that's the threshold that you see here. There is no good way of doing this. This is really up to you and exploring the data visually. If you show me these three pictures here, I would probably go for the one in the middle. Like if you are too liberal, like this looks like there are different thresholds, but they're probably connected anyway. You have like small bridges. So this seems like too liberal to me. Here we have some dirt around here, but clusters seem to be forming here, so that's good. And here it seems that we killed too much. But like I said, there is no good way of determining which vertex-wise or voxel-wise threshold you should use. But we pull that threshold out of thin air, or exploring the data, I should say. Okay. So let's go back now to surface data. So this is the unthresholded significance map. And these are like thresholds at different levels. Again, as I said before, if you lower the threshold, you're going to get like bigger clusters and they're going to start merging with each other. And if you're too aggressive, you might kill like actual true effects, right? So again, you were playing with this earlier, and if not, you're going to do it with Qdec. This then corrected map, just play with the slider and get something that looks reasonable. I would say, yeah, of these three, this is definitely too liberal. The one in the middle looks the best to me, of these three. All right, so what happens when you cluster data? You would go from, the thicknesses, you go from something like this to something like this, where you say, okay, I don't care about the p-value of each vertex anymore. I throw away the p-values, right? And now I'm going to focus on the clusters. So I'm going to focus on these guys on the right. Okay, so each cluster now has a different color. Here, because I'm using a very liberal threshold in the bottom, here in the bottom, everything is pretty much one cluster, this big cluster here. Here they have all these smaller clusters with different colors. Okay? So, like I said, toss the p-values and focus on the clusters. Now, the bigger the cluster, the more likely it is that the activation is true, right? If the cluster is very tiny, it's probably noise. If the cluster is very large, it's probably signal there. So you can build a cluster table, and actually FreeSurfer will do this for you. And here, for example, we are thresholding at significance greater than 4, which means p-value is greater than 0.0001, okay? We get a total of 38 clusters. So each cluster has a number, and each cluster has a different area in square millimeters. This is the location of the cluster, and this is the corresponding structure that you can get from the parcellation, okay? Now, like I said, smaller clusters, probably noise. Bigger clusters, probably signal, right? But the question is, where do we cut off, right? So remember, a p-value tells you how likely it is that you got your result by chance, and you want that to be small, right? So we're gonna shift completely from looking at the thickness to looking at the size of the cluster, okay? So let's say we focus on one cluster. For example, this cluster here, okay, the supermarginal gyrus, and it has an area of 440 square millimeters, okay? So the question we need to make here is, how likely is it to get a cluster of this size or bigger just by chance? If that probability is small, that means, hey, this cluster is significant. That probability is large, then this is probably chance, and you have to ignore it, okay? So the key here is how to answer this question. How likely it is to get a cluster of a given size under the null hypothesis, meaning by chance, okay? So define chance, okay? What's chance? The way we do this in FreeSurfer is simulating data under the null hypothesis. The null hypothesis is that there is no effect, okay? So there are different ways of doing this. One way, if you have, especially if you have a lot of data, a good way is like randomly permuting the rows of the design matrix. Then you essentially kill your effect, right? Another way, which is what we're going to be doing, is synthesizing Gaussian noise and then smoothing it, okay? And that's a way of simulating like a random cortical thickness. You have to smooth it because, like I said before, neighboring points in the surface tend to have similar thicknesses, right? So if you just generate like Gaussian noise, you're being completely unfair. So okay, so what we're going to do is we're going to synthesize thickness data this way with Gaussian noise and smoothing, okay? Then we're going to analyze it exactly as if it was the data that we have, okay? So we're going to threshold it at the same level, right? I'm talking about the vertex-wise threshold now. So 0.0001, okay? So we take the noise, smooth it, threshold it, and then look at the clusters, okay? And those are clusters generated under the null hypothesis because it's noise, right? So there is no effect in the noise we know. So we're going to look actually at the biggest cluster of the simulated thickness. Now, that's going to give us one random sample under the null hypothesis, okay? I can repeat this a lot of times, let's say 10,000 times, okay? And that's going to give me 10,000 cluster sizes, or maximal cluster sizes, which are distributed under the null hypothesis, right? Because it's noise, so there's obviously no effect. Okay? And that distribution is going to look pretty much like, it's going to look like this, right? Where this is a histogram of cluster sizes, this is the size, and this is the frequency. So, you know, most of the clusters are going to be smaller than 40 or 60 square millimeters, like, you know, the chunk of the mass of this distribution is here. And, you know, once in a while I get clusters that are 60, 80, 100, but that's very rare, okay? So this is my null hypothesis, okay? So now if you give me a cluster from your true data, and you tell me that the size of a cluster is like 200, it'll be like out of the chart here. I can say, that's probably significant. If you give me a cluster that is, you know, maybe has an area of like 40, then I'll say, no, there are many clusters that, you know, came out of random noise that look like this, so that's probably not significant. And mathematically speaking, you can actually compute a p-value, and essentially the p-value is the fraction of randomly generated clusters that are bigger than the cluster you're looking at. So if you give me a cluster, for example, whatever, with a given area, okay, and I simulate 10,000, and out of those 10,000, say 100 of them, which is 1%, are actually bigger than the cluster I'm looking at, then the p-value is going to be 0.01, right? If only 10 of them are bigger than the one you're giving me, then the p-value is going to be 0.001, okay? So the p-value is the fraction of simulated clusters that are bigger than your cluster, okay? Is that clear? Does it make any sense? That's the take-home message of this talk, so it's important to understand, right? Like, under the null hypothesis, I can generate data, I have a distribution, right, that looks exactly like this, where smaller clusters are more likely, bigger clusters are more rare. So if I want to say, if you want to ask my model, like, what's the probability that my cluster from my real data was generated by chance, I have to put it in the context of these simulated clusters under the null hypothesis. And the fraction of those clusters that are bigger than my cluster is the p-value. So if my cluster is very, very big, only a tiny fraction of the simulated clusters will be bigger, and the p-value will be small. And the other way around, if my cluster is very tiny, most of these clusters that I simulated will be bigger, and then the p-value will be large. This actually limits the, well, that's, shouldn't go into that. If you're interested in this, we can take it offline afterwards.
Is the simulated data based on the static data, or it's you can like randomly create simulation?
Yes. Yeah. The question is, where does the simulated data come from, right? That's exactly what I was saying about the smoothing. If you just generate Gaussian noise and you build clusters, the clusters are going to be tiny, right? So essentially, you have to smooth it with a Gaussian kernel that has a width that is matched to the typical width of neuroimaging data. Yeah. Otherwise, like I said, you are being unfair, right? It's just like generate noise, threshold it, clusters are all going to be tiny, and then you're going to get a lot of significance, right? Yeah. Also, like if you're smoothing, you have to process your simulated data the same way you're processing your data. So you have to use the same vertex-wise threshold, and you have to, if you're smoothing your thickness map, then you also have to smooth your simulated data, right? You have to treat it exactly the same way. Otherwise, you're comparing like pairs with models. So this simulation is done with MRI GLM scene, sorry, and you can do it yourself, but you will see it like later in Qdec. That is going to talk about it. FreeSurfer has already run it for a few typical values for you, so you don't have to do it. So after running this, essentially you're going to get the same table we had before, but now we're going to have a cluster p-value. Okay? And this cluster p-value is for each cluster and has nothing to do with the vertex-wise p-value. Okay? Like it says here, note the difference between the cluster forming threshold, which we used, which was 0.001, and the cluster-wise p-values that we get here. What would happen if I made this threshold more liberal? I would get fewer clusters. They would be bigger. Would the p-value be smaller? No, because when I simulate the data, I will have to threshold with the same, with the, for example, let's say a threshold with 0.01, okay? Very liberal. When I simulate the data, we'll have to threshold with that one too. And then the clusters of the simulated data will be bigger, and then this histogram that you see here will be more like this, right? So the p-value hopefully will more or less be the same. Of course, your results are going to depend on the cluster forming threshold that you choose, and that's a bit of there's no good way of choosing that one, just by visual inspection.
Sorry, so the p-value for the simulation has to be the same as the p-value?
Yes, you have to, yeah, exactly. Yeah. So if we go back to the cluster we're looking at, we can finally get the answer. The probability of getting a cluster of this size or bigger is 0.04, and that's the p-value for the whole cluster. Okay. So how to do this with FreeSurfer? This is the command line that we have, MRI GLM fit sim. We have to specify the directory of the GLM that we run. This is a very useful flag. This is has nothing to do with Qcache, but this is essentially telling you the voxel-wise threshold that you want to use in the simulation. And essentially, if you use this, you are saying, wait, don't run the simulation. Use the pre-computed values that FreeSurfer has. Okay. So if you are very whimsical and you want to have a p-value threshold, like a cluster forming threshold that is 0.012567, then you'll have to rerun the simulation. But if you don't mind using like 0.01, then you can use the pre-computed simulation and it'll be much faster. You can also do post-3 or post-4. There's another flag here which is this is the cluster-wide threshold, and the 2 spaces is the correction for the 2 hemispheres. Okay, and I'm running out of time. I'm running late already.
Sorry, we did use 2 threshold. Here we use 0.01, and cluster-wise we use 0.05.
Oh wait. That's the cluster-wise threshold. Yeah. So this is the voxel-wise or vertex-wise threshold, and this is for the cluster. So that's why we have 2 of them. Yeah. One is for forming the clusters, and the other one is for the clusters per se. So essentially, this is going to kill the clusters that have a p-value greater than 0.05. Yeah. And this is what you're going to get. You are going to get, so this is your GLM div, and let's say we were looking at the H1, it's going to generate these files. So sig MEH is the one we have already, if you remember, from the GLM analysis. And then it's going to generate this cluster MEH, which is the map of significance of the clusters. You're going to open this with preview later in the tutorial. You get the annotation of the clusters, and you get this cluster summary, which is a text file, which looks pretty much like this, with all the cluster, their areas, and their significances. One thing is that you can also, instead of using all this cluster type of analysis, you can also use false discovery rate. It's built into Qdec, and Doug is going to show you how it works, in case you want to compare results. And yeah, we're going to do the tutorial now, I believe, right? Or is it later? No, the tutorial is now? Yeah. So essentially, we're going to run MRI GLM fit and visualize the results. And then we're going to do the same thing over with Qdec, which is the pretty user-friendly graphical interface with the same data set. Qdec is just like an interactive like I said, user interface. And Qdec stands for Query, Design, Estimate, and Contrast. And it works in a very similar way as MRI GLM fit, in the sense that it's based on a spreadsheet that looks pretty much like this. It's pretty similar to the other one, where you have the subjects and the demographics. And it has a GUI that looks like this. But again, I don't want to spend too much time on this because that is going to give it a more anyway. And yeah, this essentially is going to do the same thing that I was talking about, not only now, but in the previous talk. So the whole GLM analysis and visualizing the results and correcting for multiple comparisons, but in a much friendlier way, where you can just say, hey, like this is my design, these are my continuous factors, these are my discrete factors, run the analysis, just press the button, rather than running a command, right? That's simpler. And then, rather than having to specify the contrast in an ugly text file, you will see a pop of questions will come up and say, is thickness related to age, or is the slope of this group bigger than the slope of the other group, and stuff like that, and you can just click on them and get the significance maps directly. So it's kind of nice. But yeah.